In this example, this is an example that's kind of, it's not, I don't see much application for it, but, well, you might run into other examples that in things that you do that do have applications, but it illustrates something. It illustrates, some things we might have to do in order to finish solving a problem. And here, let me make this a little bit bigger. And here's the situation. We want to find the dimensions of the largest of the rectangle of largest area that can be described under the curve y equals cosine of x for 0 is less than or equal to x is less than or equal to pi over 2. So we have, here's the graph of cosine, all right, here's the rectangle, and basically, depending on how we pick the x value, we'll have different areas. Notice right now I have the x is equal to 0 and there's no area. If we choose x to be bigger and bigger, the rectangle gets wider, all right? Okay, in the horizontal direction it gets bigger, so that would tend to make the rectangle bigger, but the rectangle gets shorter and the vertical dimension becomes less, so that would tend to make the rectangle smaller. Now someplace in here, all right, someplace in here is going to be the place where the rectangle has the very largest area, and I've graphed the area on the right so that we can see that. And if we keep going, the smaller the height gets, the lower the rectangle, the smaller the area gets. So this is the idea of this situation. And so what we want to do is we want to, let's see, look at this rectangle, and in this rectangle, notice that the area, that this dimension here, all right, I should be careful here. Somehow there is a link there. That dimension is, this dimension here is cosine of x, assuming this is x right here, and this dimension, I'm going to go up because I'm trying to get away from where I won't hit that link again, is x itself. So the area of the rectangle is a function of x. It's x, the width, times cosine of x, the height. And notice x goes from 0 to pi over 2, so this is on, we want to maximize on the closed interval from 0 to pi over 2. So it's going to have a maximum value at, again, we have a continuous function on a closed interval and bounded interval. So it's going to be maximum, remember, 3 places, at the left end point at x is equal to 0, or at the right end point x is equal to pi over 2, or at a critical point in between. And to calculate the critical point in between, what I'm going to have to do is I'm going to have to take the derivative of this. Now this is a product of x, cosine of x, so I'll have to use the product rule. And when I use the product rule, I'll have the derivative of x, which is 1 times cosine of x, and then I'll have x times the derivative of cosine, which is negative sine, so I'll have x times negative sine of x. So this will be cosine of x minus x sine of x. And we want this will never be undefined because cosine is never undefined, x is never undefined, and sine is never undefined, so this thing will never be undefined. So we want to look for where this is 0. I want to look for where that's equal to 0. Now this problem we could not solve using trigonometric or algebraic techniques. And notice the reason why I say that, because this is something that you'll run into from time to time. Notice that this variable x is the input to sine, all right, and input to cosine. It's input for the function like that. It's also it also appears outside of the sign. It appears independently of the sign as a multiplier times sign. So typically when you have problems like that, there's no way to solve those algebraically or using trigonometric ideas. The same would be true if we had something in an equation like x on the outside and x in the natural log. We'd have trouble solving that. But what we can do is we can use numerical techniques, and then I've just gone to Wolfram Alpha, and I've typed in the equation that we're trying to solve that set the derivative to 0. Cosine of x minus x sine of x is equal to 0. And notice I get bunches of solutions. But I get one that's this one here, 0.8603 is between 0 and pi over 0 and pi over 2. So I'll have this as this as x is equal to 0.86. I think that was 0.3. And maybe I should say is approximately that big, because it's that won't be an exact answer. So we'd have that. All right, now if we look at this, all right, if we look at this, we want to find the dimensions of this rectangle. Well, I guess what we can do is we could take and look at a second derivative at this point. All right, but and I'll let you do that just to find out. But the thing is, if we look at this if I just look at x equals 0, and remember a of x is equal to x cosine of x. So at x equals 0, I have a of 0 is equal to 0 times the cosine of 0, which is 0 times 1, but that's still 0. At pi over 2, the other endpoint, I'd have a of pi over 2 is equal to pi over 2 times cosine of pi over 2, but that would be pi over 2 times cosine of pi over 2 is 0, so that would still be 0. All right, and then I'd have x is approximately this 0.8603, and here I have a of 0.8603 is 0.8603 times the cosine of 0.8603, and since this is between 0 and pi over 2, x is someplace between 1 and 0, all right, not including the endpoints times this is definitely positive, so this will be the maximum. Now to ask us to find the dimensions of the rectangle is going to be, if we draw it, the rectangle is going to be x equals 0. I should keep saying approximately, because that's not an exact answer, 0.8603 units wide, and this dimension is going to be the cosine of 0.8603. And that, I'll let you evaluate the cosine of that. Be sure that remember you're using radian measure here, because we've done calculus on this. So that would be the solution to this problem. But notice here we'd have to use some computational techniques to find the critical points.